I'm going to briefly discuss the Freeze-Thaw performance. This is a preliminary study we've done. It's an ongoing experiment. So I would like to thank my PhD student, Jafar, for this work. So we all know the motivation, the CO2, the alternative material we are looking for, but we need more data on the long-term performance, right? Specifically for this project, we are looking at the cold environments, and the reason for that because majority of the country we're going to have this issue, and considering the climate change, it's going to be more problematic, right? So we need to really understand if we want to use widely in this type of regions. I'm not going to discuss what is the CSA, so I'm sure all you know right now. One thing I'm going to point out here, basically regarding the OPC system, when we are looking at Freeze-Thaw performance, what are the important factors, right? One is the permeability of the material itself. If we are using the air entrain system, the air quality of the air system, right? And lastly, the degree of the saturation, right? As I showed you at the right side, we fill in the capillary pores, gel pores, and then start filling the air voids, right? The secondary absorption rate, and when we reach that critical degree of saturation, then we're gonna start seeing a damage due to the Freeze-Thaw. So how about the CSA? Really, can we simply just apply any type of the testing to look at the performance of the CSA regarding the Freeze-Thaw? Some preliminary tests showing that the performance is different, right? Here at this side, I'm showing the 666, ASTMC 666 experiment. So CSA performing or failing at even higher air content. At the right side, this is a work from my PhD. Basically, the permeability is different, right? So these are objects of our study. Again, this is a preliminary result I'm showing. The result I'm showing is more for non-air entrain system, not air entrain system. So we want to compare this performance of the CSA with the OPC. And also, we want to connect this Freeze-Thaw performance to the pore size distribution and transport properties. So this is the experimental plan we had. We made paste and mortar sample with different water binder ratios, 0.4, 0.45, and 0.5. We used the barytic calcium sulfoaluminate, and for mortar, we replaced we used the 55% volume of aggregate in the mixes. We use the citric acid as a retarder, and we cure the sample in a sealed condition for 28 days for testing. So first result I'm going to show is the pore size distribution from the nitrogen sorption test, right? So we use this experiment to look at the desorption isotherm, and using the modified Kelvin basically equation, we can get the pore size distribution. So at the left side, you are seeing the OPC system, at the right side, CSA system with different water binder ratio. So there are a few basically conclusions we can make from this. One change in or shift to the left side you are noticing in the CSA compared to OPC in this peak. So we have a larger volume of the smaller pores, let's say less than 10 nanometer in our CSA system compared to OPC system. The distribution is narrower for the CSA compared to OPC, and in general, CSA showing a higher pore volume in all of the water binder system we tested. This is the basically total pore volume. You see the trend, the CSA giving us a higher. These are 28 days again sealed cure system. The porosity from the gravimetric method, again, pretty similar trend you are noticing here, so I'm going to move quickly here. Okay, absorption based on ASTM 1585. So if you look at or compare the OPC system to the CSA system you are seeing at the right side, when we have higher water cement ratio, 0.5, 0.45, we are seeing a higher secondary absorption rate in case of the CSA. So around 4 or 5 days, we are reaching the other side of the sample, right? But in case of the lower water-cement ratio system, we are seeing a better performance in the CSA samples. So later on, we're going to come back to this when we are discussing the Freeze-Thaw performance. And the reason for this higher, basically secondary rate in case of the higher water-cement ratios is connected to, again, from my PhD study, Amir discussed a little bit, basically the interconnectivity of the system, right? So the other observation we had in the CSA samples, this at the initial stage, really we don't see that much difference between different water-cement ratios. And if we compare this with what we get from the pore size distribution, around this range, which the voids that are filling first, we don't see that much difference either. So we think these are correlation between these two. We also use the electrical resistivity. Raul discussed about this, right? We get really high values while we dry the sample. We use the calcium lime water basically, but still our data not basically reading what we are seeing from the absorption experiment, right? And the reason for this, use the formation factor, right? So this is a work we done with the Georgia Tech. So at the left side, you are seeing the formation factors, right? We are normalizing with the pore solution resistivity. So you see comparable results between the CSA and OPC when we use the formation. And if we want to use basically this information to get the interconnectivity of pores, that's what you are seeing at right side, right? We have higher interconnectivity of the pores in the CSA compared to the OPC system, okay? For Freeze-Thaw performance, we use the thermomechanical analyzer, what you are seeing here at the top right side. We have this chamber controlling the temperature. So we move from the room temperature to -4 AC, and then we come back to the room temperature. So that's the profile you are seeing here in the red lines, the dashed lines, how we change the temperature. So by changing this temperature, we can look at the length change, the strain in the system. So that's the basically profiles you are seeing here for blue, which is the OPC. The green one is the CSA. So the left side, I have 0.5, the higher water-cement ratio system. Right side, lower water-cement ratio system. So what we are observing here in the higher water-cement ratio system, the CSA performing worse, right? We get higher expansion, we have higher residual strain because we are not coming back to zero strain we started from. So that residual strain basically connected to the damage from the Freeze-Thaw. But at the right side, things are opposite, right? The performance for the CSA, I mean, both of them doesn't really have a residual strain, but even CSA showing a lower strain while given these temperature ranges. So these are paste samples. We've done some mortar. I don't have the data here, but even in mortar, CSA is performing better. So again, if we want to connect this to the pore size distribution, the secondary hump we are seeing here, this is because we are getting we have this peak at the lower pore size distribution for the CSA, and for freezing this water inside the smaller pores, we need a lower temperature. So that's the reason for basically this second hump we are noticing in the CSA compared to OPC samples. The CT values, the coefficient of thermal expansion for CSA is higher compared to OPC in both systems. So very quick conclusions. The pore size distribution is different, right? As I showed in the previous images, we shift to the left side, smaller pore size is the peak. The absorption data, we see that the higher water-cement ratio system giving us a higher absorption rate, the secondary rate. Formation factor is the better way to use for get an idea about the interconnectivity of the pores. The Freeze-Thaw performance, higher water-cement ratio against CSA not performing well, while the lower water-cement ratio, they are performing satisfactory. And lastly, the CTA for CSA is higher compared to OPC. So that's all I have. Probably have time for one question.